Right, let's get it started. Hello everyone, welcome back to Dynamics. So over the last two lectures, we have been talking about Newtonian kinetics, and in the first lecture, we talked about Cartesian Newtonian kinetics in X and Y direction. And yesterday, we started curvilinear Newtonian kinetics using tangent normal coordinate system. And today we will be talking about the curvilinear Newtonian kinetics using a polar coordinate system, which are and theta. So let's see how this will work in r and theta coordinate system. So usually the problems is something like you have a bar, let's say, something like that. Let me make it a little bit smaller. It's like an hydraulic arm that keep changing in length, and this bar is moving on a path. So let's assume that this, if we make it something like that, and usually this is our XY coordinate system, and R is this length. This is R vector, and R is keep changing as this point is moving on this curve, and this will be changing with the angle theta. So this is the direction of the increasing angle theta, and this is R vector. So let's make R vector maybe in blue, like this. And we need to study the forces on this, like assume that this is a blue surface, like a surface at this point is attached to move on the surface. And we need to study the forces on the surface. So let's assume that there is a motor here, and this motor gives this arm a velocity, like say omega or theta dot. And the arm will exert a force on the surface. So here's a new type of force exerted by the arm, and it's always in the theta direction. So if the arm is moving in this direction, so here is the force exerted by the arm, and let's call it B. And also there will be a normal force exerted by the surface on the arm. So, and as we discussed before, that the normal force is always in the perpendicular to the surface. So, and when we say perpendicular to the surface, we need to find the tangent in the normal coordinate system. So the tangent should be, let's draw it in this color. Here is the tangent, and here is the normal coordinate system. So the tangent is always tangent to the curve, and the normal is perpendicular to the tangent in the direction of the center of curvature, and both have an angle at 90 degrees. And as we know that the normal force exerted by the surface on the arm is in the positive or negative n direction. But in this way, the surface will exert a force like this in this body. So this will be n, it's perpendicular to the surface. Like imagine that we have a surface like this, and we have a body rested here, and the weight is going down, and here is the normal force perpendicular to the surface in the opposite direction of the weight. And if it's also, there's a slope, and here's our body, and here's our weight go down, also the normal force that the surface exerts on the body is perpendicular to the surface. So the weight is always vertical in the negative y direction or with the direction of the gravity. The normal force is perpendicular to the surface, and also we studied the spring force, which, like if we are saying that the particle here at the end of the spring is moving this way, so this is the spring force. If the particle is moving this way, so here is the spring force. So this is about the spring. We studied all of these in the first lecture of the Newtonian kinetics. And here's it shows the tangent and normal, and here's the forces that we have, and it depends on the problem. If it's like if I'm telling you that this arm is vertical, like it's moving in the side view, so we will be having a weight going down. Like if here, like let's assume that there's a weight at this endpoint, so there will be weight going down. But if I'm telling you that the XY is the plane, is the table, so this XY is the horizontal, so the weight is not going in this way. Why? Because it will be going outside of the plane, like going outside the paper down. So it will be something if this curve is something like this. So, and we are saying that this is our point. So the weight will be going down, and let's assume that here is, I want to make it 3D. So it will be like, let's draw the axes first. So here is X, and here is, let's make this X, and this is Y, and this is Z. So this arm is here, like this, in the plane, like that, and here is the path that the arm is moving on. So you will have the weight will be going down in the Z axis. So here is the weight, and it's out of the plane that we are working on. So if we will work with 3D dynamics, so we will be including r-theta Z, which is the cylindrical coordinate system, and we will not touch based on these things in this course. So let's focus on the 2D, and assuming that this arm is in the 2D in the horizontal plane, and let's draw the r-theta direction and see how it looks like. So let's draw the r-theta direction with this color. So the r, we know it's in the direction of r like this. So this is r, and we know that theta is perpendicular to r, and in the direction of increasing theta. So this is how the r-theta look like, and here's how the tangent normal look like. And now we need to learn a new angle, which is the angle between the r and t. So what if, like, we delete these forces right now? So we can have some space for the angles. So if I make a horizontal line like this, parallel to the x-axis, so this angle will be theta, which will be equal to the angle down there. And also, if I have an x, like a y-axis here, the angle between y-axis and theta will be also theta as well. So right now we need to know the angle between r and t, the r and tangent. Sometimes we will need to use it in doing some force analysis, like you need the components in the r direction and theta direction, and you have some force in the tangent or the normal direction. So sometimes you will need this angle, and we will call it XC. And XC has a derivation in Hepler textbook, so if you navigate here, you will find that there is a derivation for the angle tan XC, and it's a long one. And we will just use this directly. So we have tan XC is equal to R over dr d theta. So this is how you calculate the XC. So XC will be equal to tan inverse R over dr d theta. And XC should be an angle, could sometimes be positive and could sometimes be negative. So it's in between negative 90 and positive 90 degree. So this is how we calculate XC. So let's see how can we apply this in a problem and do some Newtonian kinetics. Based on what we learned from last time, for this chapter, we know that the summation of forces will be equal to the mass multiplied by the acceleration vector. And we applied these in Cartesian and tangent normal coordinate system. But if we are talking about polar coordinate system, which is r and theta, so this will have a component of force in the r direction. So summation of FR will be equal to AR, and the sum of F in the direction of theta will be equal to MA theta. In this rule, we will have to think about the value of AR. Depends on the background that we have from the kinematics. The AR will be equal to R double dot plus R theta dot square, and A theta will be equal to R theta double dot plus 2 R dot theta dot. So in any problem, we will have to find these two values, AR and A theta. Most of the problems you will given something about R, and you will have to take the derivative of R and get R dot and R double dot. And similarly, you will given like theta dot, and you will have to integrate it to get theta and differentiate it to get theta double dot. So you will be able to account for the acceleration in the radial and transversal direction in A theta. So let's see a problem. I have a one here. Just want to move it. Let's start with this problem. So it says that there's an arm, starts from O and end at A. And this arm rotates counterclockwise. So here's the direction of the rotation with a constant angular velocity theta dot equal. So keep attention to the words constant angular velocity. That means that theta double dot will be equal to 0. And the double collar B, so there's a double collar at B that allows the rod to move on the Z radial ring, is been connected together such that one collar slides over the rotating rod and the other slides over the horizontal curve. And keep attention, it's a horizontal curve, not vertical one. So we will not be including the weight in our analysis because it's horizontal and the weight is outside the dimension of the analysis. Which is the shape is described by, so we have the R equation, so we will be able to get R dot and R double dot if both collar weight. So now he's giving you the weight of the collar, which might not, you will not use it because we will use it if we are working with 3D dynamics. determine the normal force which the curved rod exert on one color at theta equal 120 degree. So let's put the forces here. So we know that this rod, to move this way, it will exert like a force B in this direction, and the surface, the curved surface, will be putting a normal force. Just keep focus. This is in the theta direction. So here's the increasing angle of theta, and we know that this is, so let's make them in a different color. Theta direction, and this is R direction. And B is perpendicular to the rod, and it's in the theta direction. But if we are talking about the surface, we need to get the tangent in normal coordinate system. So here's the tangent, and the normal should be something like this. So here's the tangent in normal coordinate system. And we know that the force exerted by the curved surface should be in the normal direction perpendicular to the surface. So it should be something like this. Here's N. So let's actually first, before we start the problem, just like when you start the problem, you should have a strategy. So you have to check some steps and make sure that you understand the problem, like work to understand how's the motion look like and how's the forces look like before you start. So you can have some mentality how to tackle this problem. And then you draw some axes like tangent normal and r and theta, because we need to draw the tangent normal even this is a polar coordinate system problem, because we have some forces in the normal direction. So we will have to draw the tangent and normal direction, and then you will put the free body diagram and the kinetic diagram, so you can understand how the forces look like, and then you compute the acceleration. But what I would prefer first, I work my way through what is given. I have theta dot and I have r, and I can get something out of these. So I can get the AR and the A theta. So let's see how can we use the information that is given in the problem so we can get the accelerations. So here's the example. So right now, it's given in the problem that the theta is equal to 120, and theta dot is constant, equal to 5 radian per second, and theta double dot is the derivative of theta dot, and this is constant, so it will be 0. So I got theta, theta dot, and theta double dot. So let's go to r. So r will be equal to 1.5 multiplied by 2 minus cosine theta. So if you want to get r dot, so yeah, I found this issue with you guys when solving the homework. You differentiate this like 1.5, and the derivative of 2 with respect to t is 0, and the derivative of this will be negative sign, so it will be sine theta. So the negative will be multiplied by the negative, giving you positive. And you stop, but you shouldn't stop. Why? Because you differentiate sine theta with respect to theta, not with respect to t. This is d dt. So you will have to get theta dot out. So you will have to differentiate sine theta with respect to t. So it will be a theta, you will keep theta inside and get theta dot outside, like this. So the d dt of cosine theta will be equal to negative sine theta multiplied by the derivative of this with respect to t, d theta dt, which is negative sine theta multiplied by theta dot. When you plug these in, so the negative multiplied by the negative will be positive, and then finally you will have theta dot outside. And then let's get r double dot. So this will be 1.45. Okay, so it will be 1.5, and you will differentiate sine theta with respect to t. So it will give you cosine theta multiplied by theta dot, and we have another one out there, so it will be squared, and then plus 1.5 sine theta multiplied by the derivative of the second, which will be theta double dot. And we know that theta double dot is equal to 0, so all this term will be equal to 0. So let's get them in numbers. Like, let's get r at theta equal 120 degree. So this will be 1.5 multiplied by 2 minus cosine. Solving this will give you r will be equal to 3.75 foot, and you will get r dot at theta equal 120. So this will be 1.5 sine 120 multiplied by theta dot, which is 5. So this will give you 6.45 foot. This a little down. And r double dot at theta equal 120. It will be 1.5 cosine 120 multiplied by theta dot square. So this will give us negative 18.75. This is actually foot per second because this is a velocity, and this should be foot per second squared. So we got all the thetas and r necessary to calculate AR and A theta. So right now we can calculate them. We know that AR is equal to r double dot minus r theta dot square. So r double dot is equal to negative 18.75 and minus r 3.75 multiplied by theta dot square. So this will give you negative 112.5 foot per second square. And getting a theta, which is equal to r theta double dot plus 2r dot theta dot. So we know that theta double dot is equal to 0, so this term will be equal to 0. And let's calculate the second term, 2 multiplied by 6.45 multiplied by theta dot, which is 5. And this should give us 46.5 feet per second square. So we got the AR and A theta that allows us to calculate the right-hand side of this problem. So let's see how the next step. So the next step is to start to solve in one of either direction. But before I do this, let's calculate the XC, the angle between this angle, the angle between the tangent direction and the R direction. Let's calculate this angle. So I want to calculate this angle, XC. So we know that XC equal to tan inverse R over dr d theta. Just be careful, this is not r dot, because r dot is dr dt. This is dr d theta. So we need to calculate dr d theta here. So we have r equal to 1.5 divided by 2 cosine theta. So this should give you 1.5 multiplied by sine theta, and there is no theta dot because I'm differentiating with respect to theta. So this will be 1.5 sine 120, and this should give you 1.3. So we'll come here and get tan inverse. 1.3 at theta equal 120. So you will have to substitute with this. And also I will get r at theta equal 120, which is 3.75. So 3.75 over 1.3, you can do this with your calculator, and this will give you XC will be equal 70.88 degrees. So let's know why I got XC right now. So let's draw the free body diagram. So if we have the tab or the color location here, let's draw it here. And we have this, let's assume that the arm is going this way, and this is the R direction, and this is the theta direction. And for the tangent, let's assume that the curve is going this way, and this will be the tangent direction, and the normal will be perpendicular to this tangent in this direction. So this is how r and theta and Tn look like here. And we just got this angle XE. So let's see how the forces look like. We have the versed force B is in the direction of the theta. So we have B, let's extend. We have B like this, and we have the normal force in the direction of the normal direction. Like we have the normal force like this in the direction of n hat, like this n. All right, so we know that the angle between R and T is XE. So if we extend this R like this, and this angle should be XE as well from here to here. And we know that the angle between this and this angle and XE will be equal 90. And what other angle will be equal to XE? So the angle, and we know that this and this will be equal to 90. So this angle will be equal to XE. And we will know right now why did we calculate this angle and why we need it. So right now we need to write the forces term. So let's calculate in the R direction. So summation of the forces in the R will be equal to the mass multiplied by the AR. We have the mass because the weight is given. Yeah, here's 0.75 pounds. But we need the forces in the R direction. So let's see what is the forces in the R direction. We know that B is totally in the theta direction, but N have a component in theta and component in R. So if we want to analyze N, so we will have N sine XE, because we need this component in the R direction, and it has negative because it's going in negative R direction. And this is the only component that we have, will be equal the mass, which is 0.75 over 32.2 multiplied by the AR, which is negative 112.5. So right now we can get N, this negative will go with this negative, and we have N sine XE, which is 70.88, will be equal 0.75 over 32.2 multiplied by 112.5, and this will give us that the normal force equal to 2.77 pounds. And the other direction, the sum of F theta will be equal M A theta. And what we have in theta, we have B is totally in the theta direction. So we will put B here. And we have the component of N plus N cosine XE will be equal to 0.75 over 32.2 multiplied by A theta, which is 64.5. And we have N right now is 2.77. So now we can get B, which will be equal to this value, negative 2.77 cosine 70.88 plus 0.75 over 32.2 multiplied by, this will give us P equal to 0.6 pounds. So this is how we solve such a problem, and we will have to do some kinematic verse, calculate r dot, r double dot, and theta dot, and theta double dot, and get AR and A theta. Then we start the Newtonian kinetics substituting in the equation, but I will have to understand how the forces in the problem look like and how I analyze them. What is the forces perpendicular to the surface, so it's in the normal direction, and what forces in the direction of the arm, so it's in the theta direction, such as B and N. So this is how we tackle such problems. Does anybody have any questions on how to solve Newtonian kinetics in polar coordinate system? All right, maybe next time I might solve another problem. I give you like some time to practice, and we might like solve this problem next time to start with. And actually, this is the end of this chapter. And the next time after solving one problem, we might start the next chapter, chapter 14, which will be related to work and energy. So I think you guys right now are good to go to start your quiz. See you guys.